NASA's Pilgrim 1 spacecraft, which currently holds the record for the farthest distance traveled by any human-made object, has fascinated people across the globe for nearly 50 years. Since its launch, Voyager 1 has relayed vital data from the furthest parts of space, expanding humanity's understanding of the universe. However, the spacecraft's ongoing transmissions have recently faced strange anomalies that have left scientists puzzled. These mysterious signals have ignited intense discussion, making the scientific community question whether these anomalies are simple malfunctions or signs of something much more extraordinary, possibly even extraterrestrial activity. Join us as we investigate these puzzling signals and explore what could lie hidden in the vastness of space. The human desire to discover the unknown has always been the driving force behind space exploration. This deep-rooted curiosity led to the development of ambitious missions like Pioneer 1 and Explorer 2, which were among the most daring space missions of their respective times. On August 2, 1977, the launch of Explorer 2 from NASA's Kennedy Space Center marked the beginning of a transformative period in space exploration. Shortly afterward, on September 5, 1977, Explorer 1 was launched, setting off on a path that would eventually take it toward the outer planets, significantly altering its orbit and the outcomes of its mission. These two spacecraft, each weighing approximately 7,720 kilograms, about the size of a small car, traveled in separate directions at varying speeds. On December 15, 1977, a key milestone was achieved when Explorer 1 surpassed its twin in distance traveled due to the different routes they followed. Since that time, Explorer 1 has proven to be an invaluable tool in broadening our understanding of the universe, offering insights that have transformed how we perceive space. Before we delve into some of its recent groundbreaking discoveries, let's first review some of its earlier major achievements. In 1978, while situated around 265 million kilometers from Earth, Explorer 1 successfully captured detailed imagery of Jupiter. By January 1979, the spacecraft had completed a remarkable 100-hour mission, producing a time-lapse video that showcased the rotation of Jupiter. This series of 3,750 images provided unprecedented views of Jupiter's chaotic atmosphere and intricate features. During this mission, the spacecraft also discovered a previously unknown ring encircling Jupiter and identified two new moons, significantly enhancing our understanding of the gas giant's complex system. To ensure its safe journey and avoid potential collisions with Titan, one of Saturn's moons, the spacecraft performed a series of correction maneuvers. Following this, the focus of the mission shifted beyond our solar system's planets as the spacecraft was redirected toward interstellar space, traveling at an astounding rate of 325 million kilometers per year. In January 1990, Explorer 1 embarked on its mission to explore interstellar space, continuing its journey beyond the solar system. During this phase, the spacecraft achieved several remarkable milestones, including the discovery of 4 additional moons, Mimas, Enceladus, Tessis, and Rhea, and capturing some of the most iconic images of our solar system's outer regions. On February 14, 1990, at a distance of about 6 billion kilometers from the Sun, Explorer 1 took its famous family portrait, capturing stunning photographs of the inner planets. This collection of 60 images joined the spacecraft's portfolio, which also included 670 images taken during its flyby of Neptune. Explorer 2, meanwhile, also achieved impressive milestones during its mission. It recorded wind speeds that exceeded 13,100 meters per second, the fastest winds ever recorded in the solar system, providing scientists with essential data on Neptune's distant atmosphere and its moon Triton, which has surface temperatures that plunge to a frigid -391 degrees Fahrenheit, making it one of the coldest places in the solar system. Triton also displayed ice volcanoes, ejecting nitrogen gas and frozen particles up to 5 kilometers high, offering an exciting new perspective on the moon's features. These extraordinary discoveries have greatly expanded our understanding of the diverse and dynamic environments in the outer reaches of the solar system. The contributions of both Explorer 1 and Explorer 2 have been nothing short of groundbreaking. Their missions uncovered previously unknown details about the moons of Jupiter and Saturn, which had previously been thought to be dormant. These findings reshaped our understanding of the geologically active nature of these moons. In particular, Explorer 2 made history by becoming the first spacecraft to fly by both Uranus and Neptune, an achievement that has yet to be repeated. NASA employed a variety of innovative strategies to extend the missions of these pioneering spacecraft, such as shutting down non-essential systems to conserve power. The mission is expected to continue until 2030, marking the end of an era for the engineers and researchers who have dedicated themselves to this extraordinary journey. the designs of Explorer 1 and Explorer 2 showcased cutting-edge engineering. These spacecraft were built to rotate slowly, minimizing image blurring as they traveled through space. Even before reaching the outer planets, the spacecraft began transmitting detailed images of Jupiter, revealing its swirling clouds and iconic Great Red Spot, a massive storm that has intrigued scientists for decades. However, the most exciting discovery came with the identification of active volcanoes on Jupiter's moon Io. The spacecraft's instruments detected unusual signals from the moon, later confirmed by images showing towering volcanic plumes and a surface marked by intense eruptions. One of Io's volcanoes erupted with a force 1,000 times more powerful than Mount St. Helens, covering an area nearly as large as France. As the spacecraft continued their journey, they were eventually powered down to conserve energy before beginning their voyage into interstellar space. Remarkably, the images they captured did not include Mercury or Mars due to technical limitations. NASA later launched other notable spacecraft, including Pioneer 10, Pioneer 11, and New Horizons. On February 17, 1998, Pioneer 10 surpassed Pioneer 11 to become the farthest spacecraft from Earth. Despite this, Explorer 1 continued its solitary journey for an additional 14 years before finally entering interstellar space on August 25, 2012. The success of these Explorer missions was largely due to the innovative use of gravity assist maneuvers, which helped propel the spacecraft to their destinations while conserving fuel. Rather than relying solely on their propulsion systems, the spacecraft employed gravity assists, using the gravitational pull of planets to increase their speed. This technique allowed them to cover vast distances without depleting their fuel supply. As Explorer 1 approached Jupiter, the planet's immense gravity accelerated the spacecraft. Precision was essential to avoid catastrophic deviations in trajectory or speed, and these maneuvers allowed the spacecraft to navigate its journey through the solar system and beyond. Similarly, Explorer 2 utilized gravity assists from Jupiter and Saturn to reach Uranus and Neptune, demonstrating the efficacy of this technique. Reflecting on the immense accomplishments of these missions, we eagerly await further insights into the recent anomalies detected by Explorer 1. These insights helped scientists better understand how planetary magnetic fields interact with solar wind and how they shape the surrounding space environment. The data revealed that Jupiter's magnetic field is the largest and most powerful of any planet in the solar system, extending millions of kilometers into space and influencing the orbits and behavior of nearby moons. Saturn's magnetosphere, on the other hand, displayed unique fluctuations, possibly influenced by seasonal changes and the varying output of particles from its moon Enceladus, which was found to have water ice geysers erupting from its surface. These plumes not only contribute to Saturn's E-ring but also suggest the presence of a subsurface ocean, raising compelling questions about the moon's potential habitability. Uranus and Neptune, often referred to as the ice giants, surprised scientists with their unusual magnetic fields. Unlike Earth, whose magnetic field is mostly aligned with its rotation axis, the magnetic fields of Uranus and Neptune are significantly tilted and offset from the planet's centers. These irregularities led to the development of new models for understanding how planetary dynamos function deep within their interiors. The plasma wave detectors aboard the spacecraft recorded the intricate movement of charged particles in space. This data has proven essential for understanding how solar radiation and cosmic rays interact with planetary environments. These interactions, while invisible to the naked eye, have a profound impact on space weather and even influence satellite operations and communication systems on Earth. Imaging systems aboard both spacecraft continued to capture breathtaking photographs, including high-resolution images of planetary rings, atmospheres, and moons. These visuals not only served scientific purposes but also deeply impacted public perception and interest in space. For many, the photographs taken by Explorer 1 and 2 became symbols of humankind's curiosity and technical achievement. Despite being billions of kilometers away, these spacecraft continue to transmit valuable data back to Earth, although their signals are now incredibly faint, requiring deep space antennas to receive and decode the information. The Deep Space Network, DSN, with its massive radio antennas located in California, Spain, and Australia, plays a vital role in maintaining contact with these distant travelers. As fuel and power supplies dwindle, mission planners have made difficult decisions to shut down non-essential instruments and systems in a prioritized order. Each shutdown is a symbolic farewell to a chapter in scientific exploration, yet the spacecraft persist in their silent flight through interstellar space, still guided by the trajectories set decades ago. Meanwhile, back on Earth, the legacy of the Explorer and Voyager missions continues to shape future exploration. Their successes have inspired a new generation of missions such as NASA's Europa Clipper, ESA's JUICE, Jupiter Icy Moons Explorer, and planned missions to Uranus and Neptune, all aimed at unraveling the secrets of our solar system and searching for signs of life in its most remote corners. As we look ahead, the strange anomalies recently detected by Explorer 1 raise profound questions. Are they merely mechanical glitches resulting from aging equipment operating in a harsh environment, or are they indicators of unknown cosmic phenomena, or even contact from intelligent life? Whatever the answer may be, one thing is certain: the journey of these spacecraft has forever changed our place in the cosmos. Their discoveries have illuminated the darkness of space, revealed the hidden beauty of distant worlds, and reminded us of the infinite possibilities. Revealing the interactions between these planets and their environments, the plasma wave detectors helped us understand the behavior of solar wind and its effects on planetary atmospheres. One of the most remarkable accomplishments of the Voyager missions was their ability to measure the heliosphere boundary, a region filled with solar particles and magnetic fields that surrounds our solar system. As Explorer 1 approached this boundary, it detected a shift from solar wind to the interstellar medium, providing critical data about the structure of the heliosphere and its role in shielding Earth from cosmic radiation. The spacecraft revealed a distinct boundary known as the termination shock, where solar wind slows down and becomes denser. Beyond this boundary lies the heliosheath, where the solar wind interacts with the interstellar medium, creating a dynamic and complex environment. Explorer 2's journey has also contributed immensely to our understanding of the outer solar system. Its flybys of Jupiter, Saturn, Uranus, and Neptune provided crucial data, particularly its observations of Uranus's magnetic field, which was found to be tilted in a way that challenged existing models of planetary magnetism. These discoveries have sparked further investigations into the magnetic fields of other planets. These missions have not only advanced scientific knowledge but have also sparked public interest in space exploration. The stunning images of distant planets, along with the personal stories behind the spacecraft's missions, have inspired millions worldwide. The breathtaking photographs of Saturn's rings and Jupiter's volcanic moons have become iconic, encouraging the next generation of scientists and explorers. As the Voyager and Explorer missions continue to send back groundbreaking data, the ongoing exploration of interstellar space presents unprecedented opportunities to understand the very fabric of the universe. While the focus has traditionally been on the planets within our solar system, the shift towards studying interstellar space has revealed some surprising insights about the regions beyond the Sun's influence. These areas, which were once thought to be empty voids, have shown complex interactions and phenomena, some of which challenge existing scientific models. One of the most fascinating discoveries made by the Voyager spacecraft is the detection of cosmic rays that originate from outside our solar system. These high-energy particles, which travel through space at nearly the speed of light, offer clues about the processes occurring in distant regions of the galaxy. By studying the energy and composition of these cosmic rays, scientists hope to gain a deeper understanding of the mechanisms at play in distant stellar nurseries and the dynamics of galactic environments. Moreover, as Voyager 1 and Voyager 2 venture further into interstellar space, their instruments continue to monitor the density and movement of the interstellar medium, the matter that exists between stars in a galaxy. This medium, composed of gas and dust, interacts with the solar wind in a way that affects the shape of the heliosphere, the protective bubble created by the Sun's influence. As the spacecraft approach and pass through this medium, they are providing crucial data that will allow scientists to better model the behavior of matter and energy in the vast spaces between stars. In addition to exploring the interstellar medium, the Voyager spacecraft have made significant contributions to our understanding of the magnetic fields that exist beyond our solar system. Both Voyager 1 and 2 have provided detailed measurements of magnetic fields in interstellar space, offering insights into the nature of these fields and their role in shaping the surrounding environment. These findings may lead to breakthroughs in our understanding of the behavior of magnetic fields in other galaxies, contributing to a broader understanding of the cosmic forces at play across the universe. The ongoing exploration of the outer regions of the solar system and beyond is not only expanding our knowledge of space but also inspiring future generations of space scientists and engineers. The iconic images taken by the Voyager spacecraft, such as the famous pale blue dot photograph, which shows Earth from a distance of over 6 billion kilometers, serve as a reminder of humanity's place in the cosmos. These images, coupled with the scientific discoveries made by the spacecraft, have had a profound impact on how we view our planet and our relationship with the universe. The success of these missions has also paved the way for more ambitious space exploration projects in the future. With the technological advancements made during the Voyager and Explorer missions, the possibility of sending even more sophisticated spacecraft to the outer reaches of space is becoming increasingly feasible. Missions to distant exoplanets, the search for habitable worlds, and the exploration of other star systems are no longer just dreams, but are now realistic goals for the future of space exploration. Additionally, the data collected by these spacecraft have far-reaching implications for understanding the conditions necessary for life to exist. By studying the composition of distant planets and moons, scientists have gained valuable insights into the factors that contribute to habitability, such as the presence of water, atmospheric conditions, and the availability of organic molecules. These findings not only inform our search for life elsewhere in the universe but also deepen our understanding of how life on Earth may have originated. The collaboration between scientists, engineers, and institutions around the world in these missions demonstrates the power of global cooperation in the pursuit of knowledge. As the Voyager and Explorer spacecraft continue their journeys into the unknown, they carry with them not only humanity's hopes and dreams but also the collective spirit of discovery that drives us to explore the farthest reaches of the cosmos. The anomalies detected by Explorer 1 and other spacecraft also highlight the importance of continued vigilance and adaptation in space exploration. As technology advances and new discoveries are made, it is essential to remain flexible in how we interpret data from these distant spacecraft. The strange signals that have recently been detected could represent new and unexpected phenomena that have never been observed before, pushing the boundaries of our understanding even further. In conclusion, the exploration of space is an ongoing journey that continues to reveal new mysteries and challenges. The discoveries made by the Voyager and Explorer missions have reshaped our understanding of the solar system, interstellar space, and the universe as a whole. As these spacecraft continue their long journeys beyond the reach of human observation, they will undoubtedly continue to provide invaluable data that will shape the future of space exploration for generations to come. As we look ahead, the data and legacy of the Voyager and Explorer missions serve as a guiding light for the next wave of interstellar probes. Space agencies and private enterprises alike are now building on the knowledge gathered over decades to design spacecraft capable of faster travel, more autonomous navigation, and advanced communication systems that can bridge the immense distances of deep space. Innovative propulsion systems, such as solar sails and nuclear electric engines, are being tested to push the limits of how far and how fast we can travel. Concepts like Breakthrough Starshot envision sending miniature spacecraft to nearby star systems within a human lifetime, a goal that was once firmly in the realm of science fiction. These bold ideas are a direct continuation of the spirit behind Voyager and Explorer, to go beyond the known and chart the mysteries that lie ahead. But exploration is not only about discovering what lies in the far reaches of the galaxy. The missions have also forced us to turn inward and reflect on our own planet. From the distant vantage points of Voyager 1 and 2, Earth appears as a mere speck, fragile, isolated, and yet home to all that we know. The pale blue dot image, captured by Voyager 1, encapsulates a message that transcends science. It reminds us of our shared responsibility to protect our planet and to treat each other with compassion and humility, knowing how rare and precious life is in the vast cosmic arena. Furthermore, the longevity of these spacecraft, still transmitting data decades after their launch, is a testament to the dedication, vision, and ingenuity of the scientists and engineers who built them. Their perseverance, in the face of uncertainty and the limitations of 1970s technology, underscores the power of human creativity and determination. Each signal received from Voyager or Explorer is not just a scientific reading, it's a message across time, proof that our reach as a species extends far beyond what was once imagined. As new telescopes and observatories come online, such as the James Webb Space Telescope and the next generation of radio arrays, they will work hand in hand with the legacy of the Voyager and Explorer missions. Together, they will create a more complete picture of our universe, from the stars being born in distant nebulae to the potential signs of life on faraway exoplanets. The data from these spacecraft will continue to be studied for years to come, contributing to discoveries that may not even be imaginable today. In the end, the story of Voyager and Explorer is not just about spacecraft. It's about us, about our need to ask questions, to reach beyond the horizon, and to understand where we came from and where we might be going. Their journeys are our journeys. And as they drift silently through the stars, they carry with them the echoes of a species bold enough to send its dreams into the darkness, and wait for the light to return.